right, so here's our standard form. Now remember, when we're doing derivatives of trig functions or inverse trig functions, we kind of get a 6 for the price of 3 deal here, right? What's the derivative of arcsine u with respect to x?
U prime over the square root of 1 minus u squared. Yeah. Work smarter, not harder.
Okay, now don't look them all the way close. What about arctangent?
U prime over 1 plus u squared.
Okay. And then the tricky one is probably arcsecant.
It's u prime over the absolute value of u.
I can get it.
Times
Square,
the square
times the
root
square
of u
root.
squared.
Or she can just tie, it's fine.
Okay, and here's the trick, right? We can do, now look, we can be really tricky. All I've got to do to get the other ones
Just put some negatives in
exactly. Is just multiply all those by -1, right? The derivatives of the co-versions of those just have negative out front. I think they put the negative. I don't know if they put it out front or with the u prime. It doesn't matter either way. Out front. Okay. Okay. So we got a bunch of new ones then. Let's use these. Let's look at one of these applications problems. Okay, so particle travels clockwise on a circular path of diameter r, monitored by a sensor on the circle at point P. The other endpoint of the diameter on which the sensor lies, we'll call that Q, right? Let theta be the angle between the diameter PQ and the line from the sensor to the particle. So just in our picture, it's just this defining that angle as theta, right? Let C be the length of the chord from the particle's position to Q. So C is changing. Is R changing? No, R is a constant, isn't it? Is theta changing? Yes. Okay. So complete parts A and B below. So calculate d theta dc. So how can we do that? Two ways we can do this, and they're equal to it. Doesn't really matter. How can we find d theta dc?
That's a good question.
Very good question. So what do you think? You see a relationship there? Okay, we've got a trig function. Yeah. SOHCAHTOA function. So what's the SOHCAHTOA function that relates theta to C? And we want to relate it to R also, right? That's so it'd be sine. Okay, so we could do, so one way we can do this is we could say sine theta equals C over R. Okay? From there, the road diverges. There's two different paths we could take. What's one way we could do this?
Theta equals arcsine.
Okay, so we could solve for theta explicitly, right? Write theta as an arcsine, and that's okay to do. So if we do that, we get theta equals arcsine C over R. Okay, and then that's one of our standard forms that we just discussed, right? So the derivative of arcsine u, what was that again? U prime over
Square root of 1 minus u squared.
bingo. Okay, so then if we just apply our standard form, d theta dc would just be u prime. Well, what's u prime? Remember, c is the variable and r is a constant. We're differentiating with respect to c. So what's the derivative of c over r with respect to c? 1 over r, right? Isn't that just 1 over r times c? Derivative of c is 1, right? So our u prime is going to look like 1 over r divided by the square root of 1 minus u squared. Well, what's c over r quantity squared?
C squared R squared.
Good. So that's our answer. That's kind of an inconvenient way to write it. Instead of dividing 1 over r by this square root, what if we just multiplied? What if we take that 1 over r out front? And we write this as a product instead, right? So isn't that just equal to 1 over r times the square root of 1 minus c squared over r squared? And then what's the last thing we could do with that? We could do, there's really two ways we could do it. We could factor out a square root of 1 over r squared, or r is a constant, right? We could even distribute that r inside the square root, but we gotta be careful with that. If I'm gonna distribute the r is some positive constant, right? It's a radius. So yeah, r is the same thing then as the square root of r squared, isn't it? Everybody see that? So we could change this to read 1 over the square root of r squared times the square root of 1 minus c squared over r squared. Now I gotta be careful with this. The only reason we're able to do that is because r is a positive constant. Agreed? Okay. And if I multiply those two radicals together, we're just taking advantage of the property of radicals. You tell me, what's the square root of a times the square root of b?
Square root of
Right? So I take the square root of r squared minus c squared over r squared. And if I distribute that r squared, what do I get?
Square root r squared minus c squared.
Right? Everybody agree? Okay? So there's our answer. Now, what's plan B? What else could we have done? Rather than solving for theta explicitly, yeah, we could just implicitly differentiate also, couldn't we? Right? If I were to implicitly differentiate each side with respect to c, well, what's the derivative of sine hand with respect to c? Okay, I'm going to get cosine hand times the derivative of what's inside with respect to c is just d theta dc. Let's just call that theta prime, how about? And then over here, the derivative of c over r with respect to c, you already told me, that's just 1 over r, isn't it? Okay? Well, cosine theta, now how am I going to come up with a cosine theta? And I've got this picture up here that defines a right triangle.
Oh, it's just r squared. Square root.
Okay, so if we've got a right triangle, right, we can solve any right triangle. If I have two sides of a right triangle, I can solve the right triangle for the third, correct?
Yeah.
And we can always make a trade. If I have a right triangle, I can always trade any of the 6 trig functions for a ratio of sides in that right triangle, correct? Okay, so if we just filled in the one missing side up here, wouldn't this have to be if the radius or the can't talk. If the hypotenuse, how about that one? Third tries the charm. If the hypotenuse is r and the opposite leg has length c, then the adjacent leg right here would have to have a length square root of r squared minus c squared, right? And so cosine theta then is going to be the ratio of adjacent divided by hypotenuse, right? So we could trade that for and then to solve for theta dot, I can just multiply each side by the reciprocal of that, right? And isn't that just going to give me, when I solve for theta dot, then it just gives me that, doesn't it? Right? Okay, either way. I mean, I think the way that probably the textbook authors are encouraging you to use this time is probably the purple way, because we just have practiced the derivatives of inverse trig functions. But honestly, I do it this way. That's the way I love it. I use implicit differentiation. I kind of, for some reason, I would sort of avoid those arbitrary ones if I can. It just, I don't know, it seems like a lot of memorization. And once you use them a little bit, you'll memorize them just naturally, but those are the first ones I would ever forget, are the inverse trig ones, or the hyperbolic trig ones. Those are the ones you don't use very much, so, you just kind of forget those. Okay, so that's kind of just a quick review of the inverse trig stuff. So we got another, it seems like a really big step, but it's not. It's a very important step, but it's very straightforward. It's going to follow from some of the same thinking we just used on that last example. So this, we've probably done this exact problem, something very similar to this in the past, and it was pretty nasty, right? Why is that such a bad problem? Oh, I am recording. Good job. Remember it.
We have product rule.
Yeah, I've got a quotient involving a product, don't I? Right, I've got a quotient rule in the numerator. The derivative of the numerator is going to involve a product rule, and the derivative of the denominator involves a chain rule, right? And so does that, right? So I've got all kinds of quotient of products involving chain rules all over the place, right? So that's a pretty nasty derivative to take. And we've done one like that, and there's a lot of work, and when all's said and done, we're going to get an answer that hopefully is the correct one. Can anybody think of maybe an easier way to do this one? And this is coming out of the blue. What makes this so hard is the fact that I've got products and quotients and exponentiation going on there. I'll give you a leading question here. Can you think of a way that we were ever able to reduce the complexity of arithmetic operations? Arithmetic operations are just adding, subtracting, multiplying, dividing, exponentiating. What was it? Logarithms. Yeah. Right. Remember, we had a good. We talked about how when you take the log of an expression, it tends to make the expression easier arithmetically. It's going to move everything down one rung on the arithmetic operation ladder, right? So exponentiation becomes a product. Products become sums, good, and quotients become, like, let's write it down instead. So if I did the natural log, or any log, I'll just use natural log because it's easier to write. The natural log of A times B is what? So the log of a product equals the sum of the logs, right? Yeah. The log of a quotient equals the difference of the logs, right? And the log of a power equals product. I bring the exponent out front. It's n times log A, right? Okay, so that made things easier, right? Because it's much easier to take the derivative of a sum than a product. It's much easier to take the derivative of a difference than a quotient. And it's easier to take the derivative of a product than a power, right?
Yeah.
So we could take advantage of that, right? By taking a log of the right side, it makes the right side much simpler. Agree? Okay, but I can't just take a log of one side. It's an equation. You have to treat both sides equally. So I'd have to take the log of both sides, wouldn't I? If I log both sides, on the left side, I'm just getting natural log of y. On the right side, what am I going to get? And this goes back to that assignment, review assignment I gave you on properties of log. See if you can do this all in one step. I got a product, right? So I'm going to get, so log x.
Plus 3/2.
Okay, plus the log of all that, but the 3/2 can come down, can't it?
Yeah.
So 3/2 times the log of x minus 1 minus
1 log x plus 1.
Okay, and I better carve out a little space there, right? Okay, that might look worse because I've got logs introduced there, but that's much easier because now I can just differentiate term by term. And those are three pretty easy derivatives that are linked together by addition and subtraction, right? So let's deal with the right side first, how about? So what's the derivative of log x? 1 over x. Okay, now what about the derivative of log of x minus 1? 1 over x minus 1, isn't it? So this is just going to give me 3 over 2 times the log of x minus 1 when I multiply by 3/2. And then finally, how about this one? Derivative of log x plus 1? So I just get that, don't I? Everybody agree? Okay, good. What about the left side? Y prime over y, right? The derivative of log hand is 1 over hand, times the derivative of hand, in this case, is just y prime. So I'm going to get y prime over y. To solve for y prime, which is what I'm trying to find, what's the only thing I have to do? Yeah, just distribute a y through the other side. I wouldn't even bother distributing it. I would just write it as y times that quantity. Everybody agree? So we end up with, our answer is y prime equals y times all that stuff. And what is y? That, right? So our answer just ends up looking like, oops, what happened there? Our answer just looks like, if I wanted to write the final version of our answer, it's going to look like that. Times all that stuff. Make sense? Yes?
Don't the natural logs in the denominator, don't they go away when you take the derivative?
Oh, yeah, they did. What am I?
Okay.
Yeah, what are we doing? I don't know. A long break. Yeah, we take the derivative of log u, it's u prime over u, isn't it? So those shouldn't be there. You guys were probably wondering about that.
Well, the top one.
The top
The
one.
Oh, that, hold it, hang on.
Yeah, those ones stay.
That one's, those stayed,
Just
yeah.
They're put on the denominator.
Right. Yeah, so we got, there we go. But here, when we take the derivative,
Yeah, those stay.
it should have just been, it should have just been this. Yeah.
Minus 2. And 2x plus 1.
Whoops. And so, yeah, and you could distribute those twos if you wanted to. That's kind of up to you. Okay? Do you need to, I mean, we could reverse engineer this and create one big fraction out of that, but
Do we want to?
not really. You see what I'm saying? We could get a common denominator. We could, multiply this one by 2x minus 1 times x plus 1 top and bottom. Multiply this one by top and bottom by x times x plus 1. Multiply this one top and bottom by x times x minus 1. Get a common denominator and combine everything. It's not horribly hard to do. But, I mean, we would only do that if we really needed to, right? If we really needed to be able to factor the top and the bottom of the function. What if we just wanted to be able to evaluate the derivative? Plug in a value of x and evaluate the derivative.
You can plug it in.
Just plug it in, right? Turn this into numbers. Okay? So that's a perfectly valid answer, okay? Okay, what about this guy here?
Yeah.
Okay, so is this a good candidate here? Could I log both sides of this one? I mean, I could, but is it helping me?
No.
Okay, what's the difference? There's an important difference here.
Um,
Yeah, look on the right side, I've got a difference. Remember, when we talked about our properties of logs, we ran into a dead end. When we got to, the log of a power is a product, the log of a product is a sum, the log of a difference is a quotient. But there's no place lower to go than addition or subtraction, right? So if we tried to do, for example, something like this, what if we tried to do the natural log of a plus or minus b? Well, the answer is just that. You can't do anything with it. There is no property of logs to simplify that. Right? And so here's an example of one where taking a log of both sides just makes things harder. Because then I have to take a log of some great big argument and I have to use the chain rule with logs and it doesn't buy me anything, right? So here's the kicker. Because I've got this minus sign separating those two terms, I do not use that technique we just used in the last one. What do you think that's called, by the way? It's very close. It's logarithmic differentiation. What we call that.
Yes, that one was.
That's it, right? But you would only use that. You only use logarithmic differentiation to untangle knots of products, quotients, and powers. You can't do it for differences or sums, right? Now, could you have? I've got a difference in there, but that's okay because it's the base of a power, so it was useful for me to log both sides there, right? But this one didn't apply. Okay. What about that one?
Yeah.
Well, we already reviewed these, right? So we know that's what we're getting to log both sides. Is this one where we'd want to use logarithmic differentiation or not?
Yeah.
Yes.
It is, because it's exponentiation, right? There's no addition or subtraction. So if I log both sides, the log of y equals what?
2x log.
Okay? And now I can differentiate pretty easily, right? Now, otherwise, it wasn't even just, this wasn't an issue of, do I want to do it? I mean, in this previous example we looked at, if we were masochistic, we could have just gone through and done this whole derivative without using logarithmic differentiation, and ultimately would have gotten the same answer, right? Oops, this one, we don't have a choice. There is no standard form for u to the v, right? Which is what we got there. I've got some function of x to a different function of x. We have to use logarithmic differentiation to be able to even do this one, right? So what do we get then on the left? It's always the same. And then, how about over here? Product rule, right? Good, so I get 2x times, what's the derivative of log x? Plus log x times, okay, and then when all the dust settles, then that's equal to, that's just 2, isn't it?
Yeah.
Right. So 2 plus 2 log x, and if I multiply each side by y, we get our original definition of y, which is x to the 2x times this. And I could factor a 2 out, couldn't I? If I wanted to. I won't though, for a second. Well, there's really nothing we can do there, so I probably would be better taking 2 out. I was thinking we're gonna be able to simplify that a little bit, but we can't. Okay, so we probably just wanna write that as 2x to the 2x times 1 plus log x. Okay? Make sense? Okay, what are we out here? 6 minutes?
Let's do a riddle.
Say it again. Riddle. Okay.
Yeah. The first riddle.
First riddle of 2020. Okay.
Well, okay. Which doesn't make sense.
Was there a year 0
When
in?
you count to 10, you go 1, 2.
Yeah.
But that's not
Or
zero
it'd be
BC.
11.
Yeah.
If it'd be 11, it'd be in a decade.
No,
Decade, 10 years.
It means it'd be,
Here.
it was 1 BC, then it'd be.
You're counting 1 BC as
Just
0?
count 1 BC as 0.
What's
That's a
yours
JV.
take on it?
That's a JV.
So I think this is not the start of the new decade. I think the new decade starts in a year.
Because it really year 0.
No.
We gotta follow the arbitrary rules we set, otherwise nothing has meaning. Sorry.
KD, Cambridge.
Sick name Cambridge.
So I did the pirate riddle with you guys.
Yeah.
Okay, and we did the flashlight one.
Yeah.
Okay.
Bridge.
Okay. Well, I know we can do. We just have a few minutes.
That's one.
I got one for you.